Look down at the ground beneath your feet.
Yeah.
NASA, your old textbooks, and basically the entire scientific consensus will tell you that the dirt you were standing on was formed about 4.5 billion years ago.
Right here in our solar system.
Exactly. It coalesced from this like swirling protoplanetary disk of gas and dust spinning around our young sun. It is a very neat, very local origin story, you know.
It is. It provides a really comforting sense of planetary pride for us.
It really does. But today's deep dive is about to, well, completely challenge that local pride. We are pulling apart a highly speculative, honestly mind-bending research paper by Siva Chirukupalli.
Yeah, the black hole origin hypothesis of Earth.
That's the one. Our mission today is to test a radical question. What if Earth is an interstellar immigrant?
Which is just a wild concept to even approach.
It's crazy. What if the primordial material that became our planet wasn't born in our solar system at all? What if it was forged in the chaotic, violent jets of a black hole?
The stakes here are incredibly high. I mean, because we are dealing with a model that has decades of robust empirical data behind it.
Right, the textbook model.
Exactly. The standard model of local planetary formation makes a lot of sense of our current observational data. But the author of this paper is proposing a testable conceptual question based on recent astronomical discoveries.
Okay, so it's a what if, but a highly educated what if.
Yes. The burden of proof rests entirely on this new hypothesis to out-explain the conventional model. Reading this paper forces us to, examine the very boundaries of astrophysics.
It really does feel like finding out you were secretly adopted, but on a planetary scale.
That is a great way to put it.
If you are going to claim the Earth is a cosmic transplant from a black hole, you have to bring serious receipts.
Oh, absolutely.
But getting to those receipts takes a surprising detour. The paper doesn't start with telescope data or orbital mechanics. The philosophical scaffolding for this entire hypothesis is built on ancient texts.
Which is fascinating. We have to look at why humanity is even asking about primordial origins in this specific sequence in the first place.
Right.
For millennia, we have obsessed over the ultimate origin of everything, like what existed before the ordered world.
The ultimate blank slate.
Yeah, so the paper draws heavily on the Rigveda, which is an ancient Indian collection of Vedic Sanskrit hymns.
Okay.
It focuses on the Nāsadīya Sūkta, specifically verse 10.129. This text attempts to describe an initial cosmic condition using the vivid imagery of darkness concealed by darkness.
Darkness concealed by darkness. I mean, that is powerful imagery.
It really is. It pictures a state of total lack of differentiation. And from that dark, undefined primordial state, creation emerges through a mechanism the text calls tapas.
Right. And as I was digging into the cultural context of that word, tapas translates to heat or fervor, like intensity or generative energy.
Yes, exactly.
It is the energetic mechanism through which the cosmos actually forms.
It acts as the engine of creation, essentially. The profound darkness isn't just an empty void, it is pregnant with potential.
Oh, I see.
When that generative heat is applied, matter and order just cascade into existence.
The structural parallels to other ancient cosmologies are stunning, honestly, because like the book of Genesis practically echoes the exact same sequence.
Oh, definitely.
It opens with this primordial condition characterized by darkness hovering over the deep, representing a formless void. Then you have an intense, energetic burst of creation, let there be light, which initiates the ordering of the cosmos.
It's that same progression.
Yeah. The sequence goes from profound, undifferentiated darkness to immense generative energy to physical matter.
Now, we do need to establish a very firm methodological boundary here, which the paper is very careful to articulate.
All right, let's be clear about this.
Neither the Rigveda nor Genesis functions as a scientific description of a black hole.
No ancient telescopes involved.
Right, exactly. The paper does not suggest that ancient poets possessed secret empirical data. Their value to modern astrophysics is heuristic.
Meaning they're like a guide.
Yes, they provide intellectual inspiration.
So, to be clear for you listening, they offer a philosophical blueprint. We aren't saying these authors had a divine download of modern astrophysics.
No, definitely not.
But their conceptual framework gives modern scientists a new lens for asking questions about sequence and causality.
It is really an exercise in epistemological humility. The Nāsadīya Sūkta actually ends by acknowledging the limits of human knowledge, asking who truly knows how creation arose.
Wow, so it leaves the door open.
It does. By using this ancient blueprint darkness, generative energy, matter, the author asks a highly modern question.
Yes.
How does contemporary cosmology map onto that exact sequence? If we are looking for the ultimate darkness concealed by a darkness that generates unfathomable heat and matter, well, we are led inevitably to the most extreme environments in the known universe.
Black holes. I mean, they are basically the modern scientific embodiment of that concept.
Absolutely.
A black hole's gravitational field is so intense that within its event horizon, not even light can escape. It is the literal definition of an environment where darkness conceals darkness.
But, and this is crucial, the critical mechanism for this hypothesis isn't what happens inside the event horizon.
Right, because nothing comes out of there.
Exactly. The action happens just outside of it. The area surrounding a black hole, specifically the accretion disk, is incredibly dynamic.
This is where it gets chaotic.
Very. As matter is pulled toward the black hole, it doesn't just fall straight in, it spirals. It forms a massive swirling disk of superheated gas and dust.
So that is our modern tapas. The sheer kinetic energy of that material crashing into itself creates friction on a cosmic scale.
The thermodynamic environment is extreme beyond human comprehension. The intense magnetic fields winding through this accretion disk become highly twisted.
Okay, so what happens to all that twisted energy?
They can channel a portion of that infalling matter away from the event horizon and just blast it outward at relativistic speeds.
Like nearly the speed of light.
Exactly. These are astrophysical jets. Massive outflows of matter violently ejected into interstellar space. This environment is an unparalleled cosmic forge.
Let me jump in here, because visualizing this is tricky, and I really want to clear up a major potential misconception.
Yeah, go ahead.
We are not saying Earth crawled out from the stomach of a black hole.
Right.
Nothing with mass escapes the event horizon. That violates the laws of physics.
Right, the math doesn't work.
We are talking about the primordial material that eventually coalesced into our planet, being spat out by the chaotic, highly energetic whirlwind surrounding the black hole.
Yes.
Think of it like a truck spinning its tires in deep mud. The mud flying into the air isn't coming from inside the tire. It's the surrounding debris being violently thrown outward by the sheer rotational energy of the system.
That captures the mechanics perfectly. The hypothesis asks if material associated with a black hole accretion system could be expelled into space, eventually coalesce into a free-floating planetary body, and then be incorporated into an entirely different planetary system.
I mean, the scale of that proposition is just staggering.
It is massive.
It sounds like science fiction. If planetary material was ejected from an accretion disk, it would have to cross the vast, empty darkness of interstellar space to reach a totally different star.
Which is a long, very dark trip.
Yeah, space is incredibly hostile, and more importantly, it is mostly empty. The math of transit timescales alone makes you wonder if anything could survive that journey without being torn apart or just wandering in the dark forever.
Well, we used to think planetary systems were largely isolated islands, but the hypothesis shifts from ancient poetry to very modern, hard data to prove that cross-contamination happens.
Right, the recent discoveries.
Yeah. In 2017, astronomers made a groundbreaking discovery, an object named Oumuamua.
Well, the cigar-shaped one.
That's the one. Based on its extreme velocity, we're talking tens of kilometers per second relative to our sun, and its hyperbolic trajectory, NASA recognized it as the first known interstellar object observed visiting our solar system.
It just zipped through our neighborhood and headed back out into deep space. It didn't belong to our sun's gravitational family at all.
And it wasn't an anomaly either. A couple of years later, astronomers found Borisov, a clearly active interstellar comet.
Wow.
Our modern planetary defense programs are constantly tracking near-Earth asteroids, and meteorites strike the Earth's surface daily.
So stuff is constantly moving around.
Yes. By synthesizing these observational facts, we establish undeniable proof that material travels through the interstellar medium. Objects originating from outside our solar system regularly enter our neighborhood, and extraterrestrial material physically collides with our planet.
The permeability of a solar system is proven, for sure. But I have to push back on the scale of the logic here for you listeners.
Okay, let's hear it.
Just because a cosmic pebble like Oumuamua flies through our neighborhood doesn't mean our entire planetary house was built somewhere else. A stray baseball flying through your living room window doesn't prove the house was manufactured in a baseball factory.
No, that is a very fair point. You've isolated the core friction point of the paper. The existence of interstellar objects merely sets the stage, you know? It proves exchange is possible.
But not that an entire planet moved in.
Exactly. Flying through a solar system is a fundamentally different physical problem than staying there. Oumuamua had too much momentum. The sun's gravity bent its path but couldn't hold it.
This brings up the gravitational capture problem, which just seems like an insurmountable hurdle in orbital mechanics.
It's the biggest challenge for the theory.
If a rogue, Earth-sized planet approaches our sun from deep space, it's coming in hot. It follows a hyperbolic trajectory. It will whip around the sun and be flung right back out into deep space with the exact same amount of kinetic energy it arrived with. You cannot have a simple two-body gravitational interaction, just the sun and the incoming planet, that magically results in a stable, circular orbit. It violates the conservation of energy.
The physics demand that a massive amount of the object's orbital energy must be removed for capture to occur. Otherwise, it simply slingshots back into the void.
It's like trying to catch a speeding sports car with a kiddie pool. The car has way too much momentum. It's going to blast right through the water and keep going. You need an immense friction mechanism to bleed off that speed.
A very big kiddie pool.
Exactly. So how does the paper propose slowing down an entire planet?
Well, the author outlines several hypothetical mechanisms, all relying on complex, multivariable dynamics that were unique to the chaotic early days of our solar system.
Okay, so the timing matters.
Immensely. The first is multi-body gravitational scattering. Picture the rogue planet entering the young solar system and having a very close encounter with a massive body like Jupiter.
Oh, the gas giant steps in.
Yeah. In that specific geometric interaction, Jupiter could theoretically act as a gravitational slingshot in reverse.
Wait, reverse.
Right, it would steal a significant portion of the rogue planet's kinetic energy, slowing the interstellar visitor down just enough for the sun's gravity to permanently take hold.
So it acts as a cosmic brake pedal. But, I mean, that requires an incredibly lucky trajectory.
It requires perfect cosmic choreography, but there is a second mechanism. The kinetic drag of the early protoplanetary disk.
Back to the disk.
When our solar system was forming, it wasn't the relatively clean vacuum we see today. The space around the sun was choked with a dense, spinning disk of gas and dust.
Very messy.
Very. If a rogue planet plowed through that dense material, the sheer aerodynamic and gravitational drag would create immense friction.
That friction could bleed off the excess orbital energy over thousands of passes, eventually circularizing the planet's orbit.
That's the idea.
The physics, theoretically, could work under those specific chaotic conditions. But since science requires testable predictions, we can't just rely on elegant math. We have to look for physical evidence.
We do.
If we're standing on a planet forged near a black hole, we need to know what specific anomalies this paper suggests we look for.
This is where the hypothesis leans heavily into the scientific method. We cannot rewind the clock 4.5 billion years, but we can analyze the chemical fingerprints locked inside the Earth.
The rocks themselves.
Right. The paper outlines specific observational tests, primarily focusing on isotopic composition. Different formation environments in the universe leave distinct isotopic signatures.
If we treat isotopes as like a chemical passport for where a planet formed, I imagine the isotopic baseline of material forged in the extreme thermodynamic environment of an accretion disk would just scream alien compared to the standard chondritic meteorites we usually test. The tapas we discussed earlier, that immense generative heat, would fractionate heavy and light isotopes in a completely different way than the relatively cooler protoplanetary disk of a standard star.
Your intuition on the thermodynamics is spot on. The fractionation process in an accretion disk would alter the ratios of these isotopes systematically.
So where do we look?
The paper proposes searching deep within Earth's mantle and crust for isotopic ratios that defy our best models of local solar system formation. If Earth formed around a black hole, its foundational chemical baseline should not seamlessly match the rest of our local neighborhood, like the Moon or Mars.
That makes total sense. And beyond isotopes, we're looking at the way volatile elements are trapped in the rock, right? The paper discusses noble gas signatures.
Yes, gases like neon or argon. The specific conditions under which a planetary body cools and crystallizes determine exactly how these noble gases are locked into the mineral lattice. A planet coalescing from the violent jets of a black hole and then freezing in the deep cold of interstellar space would trap these gases completely differently than a planet slowly forming in a stable solar nebula.
I love that. The strength of this paper is that it doesn't hide from falsifiability. It offers a clear path to prove itself wrong.
Falsifiability is the engine of scientific progress, you know? If our deep geological evidence confirms a continuous, unbroken history of standard solar system formation for the Earth, well, the hypothesis fails.
It dies right there.
Right. Or if highly detailed supercomputer simulations prove that the aerodynamic drag of a protoplanetary disk is insufficient to capture an Earth-mass body without destroying it, the hypothesis fails. The burden of proof remains an incredibly steep mountain to climb.
Let's play this out realistically, though. If we fast forward 10 years and we manage to send a rapid response probe to intercept the next Oumuamua that flies through our system.
Okay, hypothetical.
We examine this future interstellar object spectroscopically, and we find that its chemical, isotopic, and noble gas makeup perfectly matches the deep mantle of the Earth. Does that validate the black hole origin theory?
I mean, it would be one of the most paradigm-shifting discoveries in the history of human thought.
Yeah.
It would massively strengthen the case for planetary exchange. The whole idea that Earth shares fundamental material with other star systems, but we have to separate the variables here.
Okay, how so?
It would not definitively prove the black hole origin. An interstellar match confirms the journey, but it doesn't necessarily confirm the starting line.
Ah, I see.
Proving an origin in a black hole accretion disk requires chemical signatures that can only be produced by that specific extreme environment, ruling out formation around, say, just a standard exoplanet system.
It is a remarkable intellectual journey we have mapped out today. We started by exploring the philosophical depths of ancient texts like the Rigveda and Genesis.
Right, recognizing humanity's enduring need to understand the sequence of darkness leading to generative energy.
Yeah, and matter. We mapped that ancient heuristic onto the violent relativistic jets of a modern black hole accretion disk. We plotted a hypothetical interstellar trajectory across the void, mirroring the real-life data of Oumuamua.
We hit the brakes using complex orbital mechanics.
Exactly, the reverse slingshots and protoplanetary drag. And finally, we landed right back beneath our feet, proposing chemical tests for isotopic anomalies in Earth's oldest rocks.
When you step back and evaluate why this matters, it really comes down to the intrinsic value of the question itself.
Yeah, why do we care?
The conventional model of Earth's local formation is incredibly robust, and it will likely remain the scientific consensus. But engaging with this paper proves that exploring the fringes of astrophysics prevents scientific complacency.
It keeps us on our toes.
Exactly. Connecting extreme cosmology to ancient philosophical frameworks sharpens our critical thinking. It forces us to continually test the boundaries of our models and honestly re-examine the physical ground we take for granted.
It forces us to confront the limits of our own assumptions. And I want to leave you with one final, slightly provocative thought to mull over.
Oh, I love these.
We have spent this entire deep dive focused on the Earth. But if the mechanisms for the gravitational capture of a rogue interstellar planet actually exist, if reverse slingshots and orbital drag can actually catch a wandering world, what if Earth isn't the anomaly?
That is a fascinating angle. We should definitely expand the scope of the question to the rest of the neighborhood.
Right. Look at the massive gas giants. What if some of the seemingly native moons orbiting Jupiter or Saturn are actually ancient interstellar travelers?
Just captured visitors?
Exactly. What if these massive ice worlds were captured billions of years ago, bleeding off their momentum in the chaotic early days of the solar system? They could be quietly holding on to the chemical secrets and isotopic passports of a completely different star system, just waiting for us to drill through their ice and sample their oceans.
That is wild to think about.
If our solar system has an open-door policy, who else has been living in the guest room all this time? It really makes you look up at the night sky and down at the dirt beneath your feet in a completely different way. Thank you for joining us on this deep dive. Keep asking questions.